Vale. ¿Por qué?
Es broma.
Bueno, no. Tú vas sin Wii, ¿no? Pero... Vale. Agüita, esto... Ah, mira. Tipo... No, de verdad que no, no, encima del espejo. Espera. Estoy haciendo cosas importantes. But this here. Oh, whatever. I mean, I don't think you'll see the whole screen there. Vamos a selfie. Pues...
Pero también, avisem.
Sí.
Avanza, yeah, we need to think like, what, 5 minutes?
What? Sorry?
We show...
No, I don't think there's a, like, actual...
No, there's no like a conference?
No, it's not like a conference. And the funny thing is that I think...
But then after 15 minutes we have to cut it? Like,
No. It's just, and actually it's not even 15 minutes. Everyone you ask is 15 times. So I prepare for 50, the people prepare for an hour or 45.
Okay, but then we don't cut you or we don't
No,
use anything. So we
no.
just wait for you to finish.
Yes.
Then if you take more than 15 minutes, what happens?
I don't know, that's not a problem. I mean, if you want to, I appreciate if you... Al final tú ya, a ver, dijo que era. ¿Se ve? ¿Se oye? ¿Se oye? Ah, se oye. Vale.
¿Va con latencia?
No, sí, sí.
Bueno, hay mucho ruido. No hay gate o algo. No vienes, no hay gate.
Thank you for going today to the defense of the Dani Marine team. It's my pleasure to be here as a member of the evaluation board, and I will introduce you the other members of the board, Professor Simon Fortejies-Svart from the University of Leiden, and Professor Fabio Antonini from University of Cardiff. So now Simon will present the schedule for this event.
Thank you. Yeah, it's a pleasure to be here, and we have a schedule now. We have for 50 minutes of or something like that of a talk again. Then we will question the candidate for about 40 minutes or so, maybe a bit longer, maybe a bit shorter. Then the audience is allowed to ask their own questions. I think we need a PhD to be able to do that. Otherwise, you're not allowed to ask. And then we retire and make a decision on the final verdict of the thesis. And then it's all over. Or thank you.
Thank you, Simon.
So, hello, yes, it works. First of all, thank you for coming here. Thank you to the members of the committee for taking time to read the thesis and also come actually physically here. Thank you everyone for coming, especially I'm saying this in Spanish, but la gente que no habla inglés aquí, sobre todo, gracias, porque no es chapa, es doble chapa. And yeah, so I'll start now. Me set the timer. And yes, I will be talking about my thesis, or the work I've been doing in the last 4 years. The title of the thesis is this one: Black Hole Dynamics in Star Clusters, Eccentric Mergers, and Star Black Hole Dynamics. And since I know the audience is a bit wide, the word, I'll introduce the topics a bit, and I'll go first of all through the title, and then everything's gonna be well introduced. As always, plays, this is a 3-act play. I will start by introducing the star clusters in general, and a brief introduction for those maybe in physics but outside of astro, and those not really into star clusters. Then I will move to my results, which will be the second and third part. I'll talk about the outcomes of black hole dynamics in star clusters. There's going to be black hole mergers, and there's going to be star black hole binaries. Now, onto the first part, the introduction, star clusters. I'd like to start by that definition. What's a star cluster? And there's this quote by Elliott in 2006 that says, "We know what a star cluster is when we see one." So I think a picture speaks more than 1,000 words. So here's a picture when you Google star clusters. This is NGC 1466. Yes, and onto more of a definition. A star cluster is an association of stars that are bound by their mutual gravitational force. Now these contain stars, but the stars undergo processes of stellar evolution, and these systems of bound stars can become systems that include stellar remnants such as black holes. And this is what I will talk about in basically this whole 50 minutes. Black hole dynamics in star clusters. And now for those more in the Milky Way, more interested in the Milky Way, you will say that there are two kinds of star clusters. There's the one I showed, and there's, for example, here are the Pleiades. This can be seen with the naked eye. And these two kind of clusters are globular and open clusters. Globular clusters are very massive, from let's say 10 to the 4 to 10 to the 6 solar masses. They are old, so older or comparable to 10 gigayears, and they populate the galactic halo, meaning a spherically symmetric distribution of these around the center of the Milky Way. Now, on the contrary, there's open clusters, which are lower mass, 10 to the 2 to 10 to the 4 solar masses. They're younger, and they populate mostly the galactic disk, so the plane of the Milky Way. Now, we know, or we have strong evidence for these coming from the same population, so it being formed from a continuous population. Then what we see here is basically a separation due to survivorship bias. So what I will talk about is not these very specific concepts or any globular cluster or open cluster in the Milky Way, but the concept of star clusters in general, in galaxies in general. So let me keep this one in. And first, when the cluster is formed, it undergoes processes of mass segregation. This is due to dynamical friction. Dynamical friction. Heavier objects sink to the center. And what does heavy mean? Heavy means the heavier stars that will form black holes, or the black holes themselves. So at some point, we will have that the center of the cluster is populated by an association of black holes. The center forms a subcluster of black holes. Now this subcluster is very, very dynamically active. It's very dense, so we will have lots of interactions, dynamical interactions. Now, basically, what I'll do in this thesis is to model this. And if you have to keep a slide in mind, you will remember, if you have to remember one slide from this presentation, it's going to be this one. The goal of the thesis is to characterize the outcome of black hole dynamics in the center of a star cluster. And we will do so by studying two possible outcomes. We will study, or I will study black hole mergers, so two black holes crashing into each other, which produce gravitational waves, which are detected by gravitational wave interferometers such as LIGO-Virgo-Kagra, and also star-black hole binaries, dormant systems that can be assembled in clusters, and are detectable, for example, by Gaia and other surveys. But since lots of people here work with Gaia, I will talk about Gaia. Now, from these two outcomes, this will be the second act of the presentation, and this will be the third act of the presentation. So I will now first start talking about black hole mergers, and black hole mergers, and then we'll talk about the star black hole binaries. But black hole mergers, I like to start outreach talks and general talks with the basics. And the basics are that we know that black holes exist. We see them. This is the picture. This is a supermassive black hole. I will be talking about mostly, only stellar mass black holes, but the picture is roughly the same. This is M87 star, supermassive black hole at the center of M87. And you can see here in the center there's the black hole, and there's the accretion disk around it. But we've taken a picture, so we know black holes exist. And not only we know that they exist, but we know that they merge. And when they merge, they emit gravitational waves. This, of course, was predicted by Einstein's theory of gravity, and we all know that. It's been slightly more than 10 years. So last week was, I think, 10 years since we detected them. So yeah. And they were detected by, as I said, gravitational wave interferometers such as LIGO-Virgo-Kagra. Now, if you have two black holes orbiting one around the other, they will lose some energy due to the emission of gravitational waves. This, of course, is a very old prediction. This comes from almost the time of Einstein. The energy loss by the orbit means that the orbit shrinks. So we say that gravitational waves radiate away from major axis. And major axis is just a generalization of the radius of the orbit. So the orbit decays, and the energy is removed by gravitational waves. At some point, it decays more and more and more until the black holes merge, and we detect the gravitational waves not from the whole process, but just the last fractions of a second before they merge. Now, there's a problem here, and let me show a scale that's probably familiar for all of us. This is the solar system. Sun and planets have exaggerated their size for visibility, otherwise it will be a pixel each. Maybe not the sun, but yeah. The thing is that if you have two black holes, let's say 30 solar mass black holes, orbiting around each other, they take some time to merge. If initially they are at a distance of, let's say, around here, so one black hole in the sun and the other at this distance, roughly in a circular orbit, the time they take to merge is longer than the age of the universe. Now, this is a very close distance in astrophysical terms, but not only that. The black holes, these black holes are formed from the death of massive stars that undergo giant phases. How large are the stars that produce black holes in their giant phase? They're way larger than this. So for the specific processes, they're roughly this size. So you can see, I mean, it doesn't even fit in the picture. So this is a problem. How do we have two black holes in such a close distance, so a closer distance than this, when the progenitor stars are this large? Well, if that's a problem, that's the solution. So either there's some process that makes the black hole be born together, be born these very close, or some mechanism that drives the black holes together. And to put this a bit more, let's say, scientifically, we say the origin of binary black hole mergers has two different channels. We call them the isolated and the dynamical channel. In the isolated channel, basically, we say that black holes merge. So the binary black hole is formed from a binary of massive stars that undergo some processes of binary star evolution. I'm not entering into details here, but it's usually, or in some cases, it's argued that both stars actually, let's say, form a common envelope evolution, so their gas is shared between them. I'm not entering into details here. I'm just saying that, mentioning that this exists. And this evolution of binary massive stars form a binary black hole, and then this binary black hole, after some delay due to gravitational wave emission, it merges. Now, this is the same that they were born together, but there's also the channel, the dynamical channel, where there's some mechanism that drives them together. And what separates the channel, there's two sub-channels, and what separates the channels is what is the mechanism or what external influences drive the binary to merge. In the star cluster channel, which is the one obviously I'll be talking about in the thesis, we have that either the binary black hole is assembled via dynamical interactions in the center of clusters, or there's some mechanism, the interaction with other stars or black holes, that drive the black holes closer together, and they merge because of that. The merger is triggered because of that. Just to mention, there's also other sub-channels in the dynamical channel. For example, I've shown here the active galactic nuclei, where the mechanism that drives the black holes to merge is the interaction with gas in an active galactic nuclei, or the interaction, the third body, let's say, influence of the supermassive black hole in the center of the galaxy. But I will be talking about star clusters. Now, why care about the origin of the origin of binary black hole mergers? We have lots of data coming from the LIGO-Virgo-Kagra collaboration. This, for example, the merger rate as a function of the mass of the heavier black hole. And you can see here there's merging black holes from lower than 10 solar masses up to very high value. And this distribution is non-trivial. It has some peaks, it has some decays, etc., etc. For now, no single channel can predict the whole distribution. For example, the isolated channel is very efficient at producing these low mass mergers, but not so much, or it needs to be tinkered with a lot to produce very high mass mergers. Now, understanding one of the channels is key to understanding the whole population, and is also key to understanding the rest of the channels. For example, if we find the dynamical channel, or we have evidence that the dynamical channel is very efficient at producing these kind of very massive mergers, this teaches us about binary star evolution, because then this channel needs only to predict the low mass mergers. But this is just an illustrative point. This is just the mass. There's also all the spins, mass ratio, etc., all the and all the degeneracies between them. So exciting news, but just to compare this with the observations. Now, this I'm talking about kind of a population level study. But given a single gravitational wave, do we know, if we detect one, do we know whether it came from the isolated or the dynamical channel? In general, we cannot. We detect only the fraction of a second just before merger, so we cannot separate both channels. Now the question is there any, let's say, smoking gun signal that the merger came from one of the channels? The answer is yes, obviously, otherwise I wouldn't be talking about this. So how to separate both channels? The eccentricity. Now as a summary, what I will introduce, first of all, gravitational wave, as I said, reduces the semi-major axis of the orbit, so shrinks the orbit, but also is very efficient at circularizing it. And this is a plot just to show you. If we have a binary of black holes that start orbiting at 1 AU, and initially they have a very high eccentricity, 0.9, 0.99, and 0.999. As they merge, or as they close together, as they inch together to merge, they reduce their eccentricity extremely efficiently. Now, what we detect is just barely the last fraction of a second in this line. So, basically all mergers, we detect them with an eccentricity that's below the detectable threshold. I don't think we can detect anything below 0.1 eccentricity. So we really, in order to detect a merger as eccentric, in order for a gravitational wave to have eccentricity, the initial binary must start at a very, very, very high eccentricity. I'm talking greater than 0.999. Now, this is not possible in the isolated channel. In the isolated channel, the binary evolves for a long time before merges, so the eccentricity is radiated away very efficiently, not detectable by the time it merges. It's only the dynamical channel that some eccentric mergers can be produced if the binary is assembled with an extreme eccentricity. So basically, the binary is assembled and it merges in the first passage, so almost head-on encounter. So if we find an eccentric gravitational wave, we know it necessarily comes from dynamics. Not all dynamic mergers are eccentric, but if it's eccentric, it's dynamic. So that's why we're interested in understanding eccentric mergers, and this is what I study in my thesis. Now, onto a brief experimental introduction. Please don't get scared about experimentalism. This is a gravitational wave. This is what we detect. Basically, with a lot of noise. Basically, we see deformation in space-time. There's an amplitude, and this is a function of time, and this is what we detect, the fraction of a second before the merger. As you can see here, this is where in black. This is where the black holes orbit one another. This is when they are inching together, and this is the moment of merge. And this is some relaxation after the merge, so-called breakdown. Eccentricity is very hard to detect because it's just a modulation in red, a modulation of this signal. We have no definitive proof of that an event is an eccentric and it has a very definite value for the eccentricity. But there are very strong claims that at least some events are eccentric. But as I said, the data analysis is extremely complicated. So yeah, and I'm not entering into this, but just to illustrate it. This, of course, can also be related to the M1 plot. If we see that, for example, all the eccentric mergers are very massive, this is to show that dynamics produces the most massive black hole mergers. Now, back onto dynamics. We talked about the origin of binary black hole mergers, but in dynamics was the origin of eccentric binary black hole mergers. And one could think that, okay, I will simulate we see the very dense centers of clusters, and there's all these black holes going around, it's very dense, because two black holes encounter each other almost head-on, and they merge, and it can be possibly eccentric. This is what we call a single encounter. And for particle physicists in the room, you will be very happy to see Fermi-Golden's rule. Otherwise, it's just the interaction rate. This can be calculated very easily from the cross-section. We can define a cross-section for this process, just of the two black holes going together, the number density, the center of clusters, and the relative velocity. Now, this is a rather easy calculation, but the thing is that for two black holes to merge, they have to pass within some Schwarzschild radius. The Schwarzschild radius of a black hole, one of these black holes, is some tens of kilometers. So this cross-section is some tens of kilometers squared, but yeah, hundreds of kilometers squared. So this process really does not happen. This process is very, very unlikely, just because of the extremely small size of the black hole. The leading term for the merger of the production of eccentric binary black hole mergers includes binaries. Right. This is a binary single interaction, so interaction of a single black hole with a binary. And why is that? And I also think, if I said before that the picture is worth a thousand words, here's a video. Works? Yeah, this is a binary single interaction, this is a binary of black holes, and this is a third black hole approaching. And now the cross-section for this process is much larger. It's of the size of the binary, which is some AUs, which is way longer or way wider than kilometers. And this is also a very chaotic process. In all these chaos, you can have a close approach of two black holes, and these two black holes can pass within some Schwarzschild radius and then merge. So yeah, the leading or one of the leading terms for the production of eccentric binary black hole mergers is this binary single interaction. It still goes. In this case, one will separate the way, but you can also trigger a merger. Now, I've talked about binary single interactions, but if you have binaries, what about binary interactions? It's more or less the same. Here's the illustration. There two black holes, a binary of black holes here and one here. It's very small because it's in scale, but the idea is that they are less common than binary single interactions just because of the low binary fraction, but each interaction is way more chaotic. So overall, it balances out, and we have roughly the same mergers from binary and binary single interactions. But yeah, here there's a merger in all of these cases. There's a merger with some eccentricity. Now we know that these binary black holes undergo binary black hole interaction. Sorry, it's a bit wordy, but how it is. How are these binary black holes produced? One could say that, oh, we form a cluster, and the binary of stars produces binary black holes. These undergo binary black hole interactions, and then you have some merger. This is what we call the primordial binary black holes. These are formed from massive star binaries that form when the cluster forms. So basically, and this is the naive approach, if I have double the initial binaries, I will have double the number of binary interactions compared to binary single interactions. Other possible channel, I'm putting here both hypotheses. Another possible channel is that the binary black holes that undergo binary interactions are formed dynamically. So from three previously unbound black holes, they can come into a closed region, and two of them form a binary black hole, and the other is separate. These are also called three-body binary black holes because they are formed from the interaction of at least three bodies. You cannot have in Newtonian gravity, you require, because of conservation of energy and momentum, you require at least three bodies. Usually it's more, but well, the idea is that there's a dynamical formation of binary black holes. We call them dynamically or three-body binary black holes. Both nomenclatures are either used, so I will kind of switch between both. This is not a novel idea. This was proposed by Douglas Kevin back in 1975, and he proposed what it's called the dynamical binary black hole life cycle. So we said that they form via the interaction of at least three previously unbound black holes, and then they evolve via binary single interactions. Here in this model, he only included binary single interactions, and in my first project, I extend this to include binary interactions. Now, the interaction of this binary undergoes binary single interactions, and if it doesn't merge, which was not talked about in Eccentric 5, the binary tends to shrink. It tends to become tighter. This is just because of conservation of energy and momentum. This, in turn, the energy that's taken away, or the more negative binding energy of the binary, means that the third black hole is accelerated, and also the binary gets some recoil kick. Given that the binary becomes more and more bound, and the energy loss is a fraction of the binding energy, at some point the binary is sufficiently tight that the next interaction just kicks it out of the cluster. And this finishes the process, and then there's another three-body binary forming and evolving, etc. Otherwise, the binary can be so tight as to merge. This wouldn't be eccentric, but there's also the possibility of mergers here. Now, this does not, the first thing that we wanted to test here was, and this is, I'm introducing here my first paper with this plot, demographics of dynamical binary black holes. What we wanted to study was, in order to study the mergers, we wanted to know the population of these dynamically formed binary black holes, and also include binary interactions. From the models of Heavy, single mass models, so assuming the cluster was only single mass, we extended this to clusters consisting of stars and black holes, and we tested, and we wanted to find the number of dynamical binaries. Now, what he says or the models are these red and gray lines. So gray is the theory, red is the theory plus some correction. And then we run some simulations of clusters, some very simple simulations. And the crosses are the x's are the number of binaries or dynamically formed binaries in our cluster. So blue is within the half-Hash radius and black is within the core radius. Yes, as I said, the line is the classical theory from Haley, which predicts, let's say, a handful of these dynamically formed binary black holes. And the number depending on the total number of, first in small the stars, but also on our models depending on the number of black holes. And these the simple embodied models. In the simulations, what we find is that it's kind of a boring result in the sense that there's only one of these dynamically formed binary black holes. And as you can see here, and given the loss of the audience at the back, this does not match. This is a very bad plot because the models do not reproduce the data, as I've seen here. What are we missing? So what we found in our first paper is that this model that has been widely used since 1975 has missing ingredients. We're missing ionization in binary-binary interactions. As I said, we're missing binary-binary interactions. The most likely outcome of a binary-binary interaction, when there's two binaries, is that one becomes a bit more bound and the other ionizes. It separates. I'm talking ionized because of the equivalence with chemistry, but it's the same idea. Two binaries interact and only one survives. The model that we propose is that the rate of creation of dynamical binaries, of three-body binaries, is correct, but you form one, and then as you form further dynamical binaries, these undergo binary-binary interactions with the previously formed dynamical binary. And then only one of these dynamical binaries remains. This explains why the formation rate is correct, but also the models only have one dynamical binary. It's just further ones are ionized. And what does that mean? This means that there's a high rate of binary black hole interaction, binary interactions. And this can be important for mergers. Now, still on our first paper, we wanted to test what's the smoking gun proof that this happens. Smoking gun signature of binary interaction is the formation of dynamical black hole triples. So our simulations do not have initially any triples, do not have initially any binaries. The simulation forms binaries, so there's dynamical binary formation, but the only way to form a stable triple is through binary interactions. Why is that? It's rather simple. So if we have a black hole triple, just a binary black hole and another black hole going around, if we assume that this is stable, it's stable towards the future, so it doesn't dissociate towards the future. This means, due to the reversibility of equations of motion, it's stable towards the past. So the only way to form this system is due to the interaction of at least 4 bodies or more, in this case binary interactions. Now, what we did was just get our models and test and find triples. And this is the number of stable black hole triples in our models versus the number of black holes. We see that for all models, there is stable triple formation. This for one of the parameters, but we can, for all parameters, it's the same. So, we know that there's binary interactions in models without primordial binaries, just because we necessarily see these triples. And so yeah, we know. Now, back onto this, we know that this happens. So dynamically formed binary black holes undergo binary interactions. In our second paper, we wanted to go a bit further on that. So we wanted to test these assumption realistic models of, let's say, Milky Way-like globular clusters. So what we did, we took some cluster simulations from Caldener. These 148 cluster simulations that have been run in a Monte Carlo fashion with cluster Monte Carlo, with varying initial number of stars, beta radius, galactocentric radii, and metallicity. This also has some initial binary fraction of 5%. And these models I did not run them. It was they come from Gaia. And these models are meant to represent a Milky Way-like population of globular clusters. And we got these models and we tested what are the binaries involved in binary-binary interactions. And what they saw, and this is a key result of our second paper, is that more than 84% of all interactions are of three-body binary black holes. So, to have binary black hole interactions, you do not really care about what was the initial binary fraction of the cluster or the initial properties of the cluster. You just care about the dynamical black hole formation. Now, if you want to get the gravitational wave mergers from these, gravitational wave mergers in binary interactions, this is a very cool coincidence, or a very happy coincidence. If this all depended on the primordial binary black holes, this would be a mess to predict. We would not be able to predict anything because it would be highly dependent on the initial conditions of the cluster, the initial binary fraction, the initial distribution of major axis, eccentricity, etc., etc., and the evolution throughout more than 10 years, so it would be complicated. But if it depends only on the dynamical binaries or three-body binary black holes, this becomes much more predictable because it depends only on the cluster properties today. Because when the binary forms, it undergoes binary-binary interactions rather fast, and then these interactions trigger mergers, and these mergers happen almost instantaneously. So we are then blessed with models that have way less uncertainties, or we can predict our models are way less uncertain when predicting gravitational wave mergers from binary interactions. Now the first thing that also we showed in our second paper, and this is a plot of the interaction rate of binary-binary, so the binary-binary interaction rate compared to the binary signal interaction rate. I'm talking black holes here, depending on the number of black holes. This would give the prediction for primordial binary black holes, so if they came from binaries of stars, obviously it would only depend on the binary fraction. And this would be the upper limit, so some binary association, etc., etc. And this line is the prediction for the three-body binary black hole. So this model where there's one dynamically active binary black hole, and then there's a dynamic calculation of further ones, they are rapidly ionized. And we can see here the blue are the models, and we see here that we really mass the models, so the data can only be explained by the interaction of three-body binary black holes. And this is also more relevant for clusters, so there's more binary interactions for clusters that have less black holes. This is going to be something that's going to come up a lot during this presentation. Smaller clusters will be more important. And I will hammer this idea. We have to care about smaller clusters. Now, let's continue with this. We wanted to know the gravitational wave implications of binary interactions, so what we did was study the, let's say, gravitational wave outcomes of binary-binary interaction. While I said that the most likely outcome is the ionization, that we care about mergers and also triple formation, which can also triple mergers. As I said, binary interactions can create stable triples, and these triples can merge. How? Due to a process that's called the LIGO-Virgo-Kagra or Pontzypel LIGO-Virgo-Kagra mechanism. So you have the inner binary black hole and a third black hole going around. The inner binary black hole can, in some cases, have oscillations in their inclination and eccentricity. Now, if they have a high eccentricity, if they reach a high eccentricity, the inner binary black hole can have a very close precise, and this can trigger merger. It's shown here in the picture, but also in this plot. There's two different triples, blue and this, I think it's right. This is the inclination, the relative inclination between the orbits, and this is the eccentricity. You can see here there's some big oscillations in eccentricity and inclination, and once the eccentricity reaches a very high value, this can trigger a merger. Now the way to study the outcomes of binary interaction was to get the binary the outcomes of binary interactions is to get the outcomes the binary interactions from the CMC, so the Monte Carlo simulations, and we rerun them. And how did we rerun them? We rerun them with fully post-Newtonian n-body simulation, the tsunami code by Alessandro Tani, basically. But the thing is that I'm including post-Newtonian correction and including energy loss via gravitational waves and including all these processes. For more technical, this comes up to, I think, 3.5 post-Newtonian. And for each binary interactions, we sample the initial orientations of the binary and angles, so we have way more statistics. And what we find is that, or the first thing that we find in capture is the dependency of the initial cluster mass. Shown here is the number of mergers as a function of the initial cluster mass, and this is grid that goes as to the mass to the 0.5. So clusters with more massive clusters produce more mergers, and this is somewhat expected. But this has some details because there's way more low mass clusters than high mass clusters, right? So this is the plot of the initial cluster mass function, and it roughly follows the power law to with the exponent -2. Here it's shown roughly -2. This has some cool properties, and one of the cool properties is that there's the same mass contained within low mass clusters than in high mass clusters, just because there's way more low mass clusters. So as an example, there's the same mass in clusters in the total in the universe. There's the same mass in clusters from 10 to the 3 to 10 to the 4 solar masses than in clusters from 10 to the 5 to 10 to the 6 solar masses, just because there's way more, as I said, way more lower mass clusters. Now we have to take into account the parameter that we take that we care about is not the number of mergers per cluster, it's the efficiency, the number of mergers per initial cluster mass, or per initial cluster mass. And the efficiency is way higher at lower cluster masses. It's just the same plot as before, but divided by the initial cluster mass. So what we care about, and I said it before, and I said it again, are low mass clusters. Low mass clusters are more efficient at producing these kind of mergers in binary interactions. Then we also computed the redshift dependence of these. Here I showed the rate, the function of the redshift, the merger rate, and the cluster formation rate. And we see that the the merger rate of eccentric mergers follows the cluster formation rate. I can rescale this, so you can see it's roughly comparable. And also the vertical offset means that there's some mergers per cluster. And now this is the result that LIGO-Virgo-Kagra people care about. At redshift closest to 0, the predicted rate for mergers in these binary interactions is about 1 gigaparsen cube per year, which means that roughly 4% of all mergers, of all detected mergers, come from this channel. Let me go back to this. Now, what's the eccentricity distribution of these mergers coming from binary interactions? Actually here, this is a very technical detail how the eccentricity is computed. The eccentricity is computed when the frequency of the 2-2 mode of the gravitational wave is 10 Hz. Now this is a very technical detail that you don't really need to care about, except for the fact that it's the same definition of eccentricity that they use in the experiments up to our 3.5 post-Newtonian approximation. So this eccentricity distribution can be compared directly to the gravitational wave data. And this is what we find in our second paper, that the eccentricity is the blue are the simulations, and this is the model with its uncertainties. The eccentricity is roughly flat in logarithmic space between 10 to the minus 2.5 to eccentricity of 1. Now to triples, we see that we form very wide triples that are easily ionized. This is the distribution of semi-major axis, the distribution of eccentricities of the inner and outer binary and the triple, and these are very wide, and the eccentricity is roughly terminal, with some kind of high eccentricities because of otherwise it wouldn't be stable. And overall we compute the rate from mergers in LIGO-Cosine mechanism triples, and we see that it's about a third compared to captures. Now this I'm only talking about triples formed in binary interactions and capsules in binary interactions. But the Lie of mechanism is subdominant, so we kind of it's subdominant in our analysis. Now the conclusions of these first two papers, second act of the presentation, is that the binary black holes involved in binary black hole interactions are three-body binary black holes. These interactions produce roughly 4% of all mergers with a redshift distribution that follows the cluster formation rate, and also less massive clusters are more important, and that these interactions also follow our triples. Now the future work or current work, we want to include these binary black hole interactions in fast codes for, let's say, population synthesis, and in this case I'm working in cluster black hole binary dynamics, CBHBD for short, with Fabio, basically, developed by Fabio in collaboration with Mark. Now, I'll take a short break. Changing topics a bit. I'll talk about star black hole binaries, and since the audience is really interested in Gaia, I'm gonna call them Gaia black holes. Although there's more than Gaia, but I'll talk about Gaia black holes. Okay, I'll do another short quick introduction for those not really gravitational waves. So we jump topics. And my question is, how do we detect black holes? I've talked long about gravitational waves and need to introduce them further. And I'm being very generalistic here to say that we can also detect black holes electromagnetically with electromagnetic observations. And here I'm mentioning Gaia because how couldn't I? And also there's X-ray observation, and there's radial velocity observations, and so in general, gravitational waves and electromagnetic observations. Now, what are the kinds of black holes we detect in these with these methods? For gravitational waves, we detect black holes outside of the Milky Way and with generally higher masses or high masses. I'm talking a median of, let's say, 30 solar masses, a median. For anything that's detected electromagnetically, it's generally in the Milky Way with smaller masses, so less, around 10 solar masses. So basically what we're seeing is two different methods that observe two different populations. Now, the question is there an object that breaches both of these populations? And the answer is obviously yes, otherwise I would be talking about this. So this object is Gaia Black Hole 3. This was found in preliminary analysis of the next Gaia leaf release. This is a dormant star black hole binary, meaning a black hole and a star going around it. Dormant, I mean that there's no accretion and there's no there's no mass transfer and there's no high energy radiation emission. Now this was found in the Milky Way, but the mass of the black hole is comparable to black holes found in gravitational waves. And well, there's some properties of the binary. The star is a subsolar mass giant star, extremely metal poor, very wide orbit, 4,000 days of period, 0.7 eccentricity, and the black hole is 33 solar masses. So let me compare this back again. This is the cumulative distribution function of the black hole masses of all known black holes. In red, you see black holes found in X-rays, and in black, you see black holes found as gravitational wave sources, so LIGO-Virgo-Kagra sources. Basically, you see that these are two very different populations. X-ray black holes are way lighter, also Gaia Black Hole 1 and Black Hole 2. But Gaia Black Hole 3, which was detected electromagnetically and in the Milky Way, is very close to the median mass of the black hole detected with LIGO-Virgo-Kagra, meaning that it forms part of a bit of the two populations. So understanding, and it shows that understanding the processes that lead to the formation of Gaia Black Hole 3, the binary, can constrain the origin of gravitational sources. It's the same kind of processes. So, given this, what's the origin of Gaia Black Hole 3? First, of course, the first thing that comes to mind, the first thing to think is that it was formed in isolation. So we have a binary of massive stars, one star turns into a black hole, and that's it. That's Gaia Black Hole 3. Now this approach has some problems. The first of all is that the star has no chemical peculiarity, so that it has no weird signatures in the spectrum or weird abundances. But it should, because at this distance, it should have undergone processes of mass transfer or contamination via the supernova, so we should see some chemical peculiarities when studying the spectrum, if it had evolved in isolation. Now this was solved, no mass transfer, this was solved by saying that the mass transfer is suppressed by the extremely low metallicity. This was shown by Karim El-Badri and also Giuliano Iorio in the audience. But also, most importantly, where is this binary located? This binary is located in any way in a stream, in a tidal tail of a now dissolved globular cluster. This is called the ED2 stream. Now, if a tidal tail has formed from a now dissolved globular cluster and Gaia Black Hole 3 is associated with this stream, means necessarily that Gaia Black Hole 3 formed in a cluster. So we have to study the origin of Gaia Black Hole 3 in a cluster, in the progenitor cluster of the ED2 stream. Now this is our third paper. We search for dormant star black hole binaries formed in our simulations, or in the classic Monte Carlo simulations that I've shown before. And this, we made this cool triangle plot. This shows the binary properties, mass of the black hole, mass of the star, eccentricity and period. And all this data shown here is what's found in the simulation, this colored data. And on red, we see Gaia Black Hole 3. So, what we find is that there are objects, or our simulation, or cluster simulation, naturally and without targeting, produce star black hole systems that are similar to Gaia Black Hole 3 in their properties. So, masses, period, and eccentricity of Gaia Black Hole 3 are compatible with the cluster formation scenario. Specifically, what we find in these simulations is that the objects that are produced in a cluster that are the most similar to Gaia Black Hole 3, they produce as 3 polybinaries. So we basically argue for a dynamic conformation of these objects. Now we kind of extend our results to make general predictions about dormant star black hole binaries that are to be detected in the next Gaia release. As I said before, and I say it again, the efficiency is lower for high cluster masses. So lower cluster masses are more efficient. Again and again. Is the efficiency of producing these objects compared to the initial cluster mass. And of course we also find clusters with binaries for more star black hole binaries, although not the ones that are more similar, as I said, in these models. The ones that are more similar to Gaia Black Hole 3 are 3 polybinaries. We kind of stick our necks out and make predictions for the next Gaia data release. And our prediction is this. Our prediction is that in the stream there's only one Gaia Black Hole 3, which is compatible with what we see. There's about 10 to the 5 of these objects in the Milky Way, and this is our, let's say, bold prediction. We will find out 100 of these objects within 3 kiloparsecs in the next Gaia data release. So, quote me on this. On the conclusions of this third act, Gaia Black Hole 3 likely formed dynamically in the progenitor cluster of the ED2 stream. And clusters also form star black hole systems. Star black hole systems are a natural outcome of cluster dynamics with these numbers. And obviously excited about the next Gaia data release. We will cover a population of these systems we can analyze. Now on to my final slide of the thesis, general conclusions. First of all, I talk about eccentric inverters. They are key indicators of cluster dynamics. When we have more confident detections of eccentric gravitational waves or an eccentricity distribution for gravitational waves. We can construct dynamical models of star clusters. And also we show that we must include dynamical three-body binaries and interactions in our models if we want to predict the formation of gravitational wave sources, both eccentric and non-eccentric. Also, dormant star black hole systems, so Gaia black holes, are natural outcomes of cluster dynamics. We cannot decouple binary evolution from dynamics. We cannot study star black hole systems just in isolation. We need to include the dynamics of the cluster. And we need models for the formation of star black hole systems in preparation for Gaia DF4. And this is tangentially what I've been hired to do as a postdoc in Heidelberg with Michele. And yeah, producing models for the formation of star black hole systems in preparation for Gaia DF4 and also after the publication of Gaia DF4. And finally, I would like to highlight this paradigm shift in cluster dynamics, where these two outcomes that we studied, eccentric mergers and star black hole systems, the formation efficiency is inversely proportional with cluster mass. So, as a modelers, we are happy, we are lucky, because we need to focus on lower mass clusters, which are way easier to simulate. And with this, I finish my presentation, so I'll be happy to take the questions first of the committee and then of the audience. Thank you.
Thank you very much, Daniel, and we will start on the project.
Yes, thank you very much. You take the time to take a glass of water. Thank you for the nice presentation. We start now with questions from the committee. I think that maybe after we start.
Yeah, sure. Very general question on your first figure showing a picture of the Hilbert cluster. How do you know the stars are bound?
Oh. Okay. How do I know that the stars are bound? Observationally.
Yeah.
Okay, so you have Gaia data, you know their positions and you know their velocities. You can compute their principally you can compute their potential and you can compute the total energy of the system. And you know.
Well, maybe I can rephrase my question in a different way. So you said as a definition of a cluster, there's a bunch of stars bound gravitationally to each other. Right? So what clues do you have that they are actually from, so that they are the same population born?
They're the same population.
Yeah, and they might be bound to each other.
Sorry?
And that they might be bound to each other, forming one bound cluster. One.
In general, so it's complicated because we also talk about multiple populations in clusters. But in general, it is thought that clusters form from a single. This is very hypothetical. For a single, is this on? Yes. For a single collapse of a molecular cloud, so they should have roughly the same. All the stars should have roughly the same age and roughly the same metallicity. So we kind of know that for there's also the issue of multiple cluster populations, which I have not entered into this in this thesis. But yeah, I mean the cluster is bound just because of their from the positions and velocities of the stars. You know, otherwise it would just dissociate. Yeah, I'm not an observer. So.
So I had a, so you mentioned the eccentricity of the binary, right? And you said that it's hard to measure from
yes.
gravitational waves. So I was wondering if you could just explain a little bit more why it is hard to measure from the gravitational wave signal.
Yes, this is a bit more.
I guess because from here it seems like actually that it would be easy to
No, of course.
because of the large difference.
This Yeah, no, in this case, so first of all, in gravitational wave data analysis, everything is just flooded with noise. I don't have a figure, but everything is completely flooded with noise, so the only way basically to find, or the most efficient way to find a gravitational wave is to know what you are looking for. Basically to have a template and match that template to the gravitational wave data. This is the match filtered search. There's also the C compact wave burst thingy, but I'm not entering there. The problem with that is that as you include more parameters, there's a lot of degeneracy. And specifically for eccentricity, eccentricity is very highly degenerate, and it's not so. First of all, the leading terms are not even the mass, but some combination of the mass, and then that's the introduction of the masses, the combination of the spins, then the spins, then the parameter space is very large, and everything is very highly degenerate. In this case, the eccentricity is very highly degenerate with the precession of the gravitational wave. So it is at this level of noise and at this level of template matching, it's very hard to untangle eccentric and precessing mode. So you know that there's something that's not quasi-circular, but you don't know if it's processing or if it's eccentric. And also the fact that introducing a new parameter means adding a new dimension to your parameter bank of templates to match. So this means like a ton of simulations in general relativity, which is mass beyond general relativity, which are computationally really expensive to do. And also this is for mildly eccentric binaries, because then extremely eccentric binaries they have very way different signatures, and they're also shorter, so it's very complicated.
Maybe a related question to this. I mean, you mentioned that basically it's hard to measure at 10 gigahertz, right? What is LIGO is measuring.
Yeah.
But then I think you mentioned like future, right? Future gravitational wave experiments. We have LISA, we have DESIGO, we have other missions which will fill this gap between LISA and LIGO, which operate at lower frequencies. So then the circularization process is not so strong, right? So then you will have a much easier way. Something that you explored or somebody else explored in the literature, like detectability with these future missions?
Yes, there's some studies on this. I decided not to focus on future gravitational wave detectors just because they're future. And LISA is solid 10 years from now, 35, hopefully,
Yes.
hopefully. So yeah, the current deadline also moved a bit. So I prefer to do, let's say, to focus on current experiments that are working now. But yeah, it's also a very worthwhile endeavor to look for.
Well, I think there's a Chinese mission planned for about 2030.
Yeah, the TNT,
Not that
is
far,
it?
yeah.
Yes, yeah.
So,
But also, there's also a very cool effect on that, because if this comes from a binary single or binary interaction, maybe you have an acceleration due to the third and fourth black holes of this center of mass of the merger, and maybe at those frequencies you can also have the effect. This is being explored by the group in Copenhagen. What they call it environmental effects of gravitational waves.
I think we should not neglect this, right? Because you need templates for those missions as well. And these template models are made. I think for example, the linear simulation, that would be great to have.
Yeah, no, the templates are so my simulation, they go up to 3.5 post-dependent terms. So, while it is sufficient to roughly match this early part, it's definitely not enough to match this. It would be extremely computationally intensive to do that. There was this project that we started with Tomás Andrade to try to match my initial conditions to of these final conditions and, let's say, have a physics or an astronomy informed prior on the template bank generation, but this project, well, Thomas left, so this project kind of was left in the middle state. But all models of eccentric, all templates of eccentric gravitational waves are sufficient to search for this, and you don't really need our priors. I mean, they would be really useful to target the most likely scenarios, but you can just simply get them from the eccentricity distribution they showed before. Yeah.
Can you show the first figure from your first paper?
Yes.
The one showing the number of binaries. Yeah. A function of random stars. Yeah. So it wasn't exactly clear to me from your thesis and from here which points I should actually see the blue and the black. And if I believe the blue ones, right, then that means that the models are producing the number of binaries compared to the theoretical application and high-end cluster masses.
The prediction are, I would trust I think the red line is more correct. Well, it's more accurate, the model, or the model considers more physics. And you should consider the blue points, which is the dynamical black hole binaries that are within the half-mass radius of the cluster.
Okay, so you talk about why the model overproduces the number of binaries compared to the blue one, but why don't you also talk about why the blue points are both the red line or high masses, high number of stars, compared to the 4 solar masses?
This is mostly with all the uncertainties, and since the model actually the theory does is consider the black holes within the core radius, so it's actually with the under predicting, because it considers, or the simple model considers that the black holes leave the core for only the time that they spend outside of the core. This very simple model is negligible. So in this case, with the theory, we're just over predicting in any case. But the general point is that it doesn't work, because the dependencies are all wrong and the numbers are not correct. I mean, originally this plot was just the blue and red, and you would see the points going this way and the line going this way, so it's not a correct model. And our solution is that, and it's also proved by the existence of triples and the CMC models in general, the rates.
Thanks. I enjoyed actually reading your thesis.
Thank you.
I'm very much impressed by your image. It's a little better than mine. You have a good teacher.
I do. I wonder who taught him.
Yeah. So I'm going to go one step back actually, and to the global cluster. You say there's a continuum of open to global cluster. How do you know? Why is it not just a bimodal distribution, and is it more complex than just the sort of Schechter function or Power function or so? You have this nice plot from this.
I know. Okay, that's what. Wait. Makes sense.
There's still discussion on whether or not there are basically two populations of clusters which are born in the disk or which are born in a halo, and they born at completely different moments in time. The universe looks completely different. And if you say that Neanderthals are the same as humans today, where does it come from?
In my thesis I take it as a given, basically. But basically, what I would say from model's perspective is that I know that if you have a very low mass cluster in the Milky Way disk, it is dissolved rather rapidly. So the idea is that if I have, and I know this doesn't go the other way around, but if I have a continuous population from the beginning, then at the end I will have this open cluster and global clusters.
I guess my problem is what is in the middle, right? You don't seem to see, as far as I know, these sort of missing.
The missing ones are
middle one clusters.
the missing ones are dissolved in the throughout the evolution in the.
Let's put it this way. I mean, if you look at R136, which is 5 solar masses or so, 60,000 solar masses, it will live for a billion years or so before it dissolves. So where are the half-billion-year-old 5 times 10 to the 4 solar mass clusters? Is there a missing population? Relatively young, relatively massive star clusters.
There's observations of young massive clusters in.
Young, but I mean not so young. Let's say 100 million years old, maybe half a billion years old.
I'm not sure. I'm not.
Because they make it very important here, right, in the picture. I mean, it's the type of clusters which are potentially common
Yeah.
and potentially make a lot of gravitational wave sources. But sort of missing in the observations, I think.
Not sure.
Sure. So I think what I see a lot in gravitational wave research is that everybody has his own favorite scenario for making binary black holes, and you have making binary black holes from binary evolution, and the single, I don't know how you call it, but it's maybe some weird terminology here, but you have this galactic nuclear disk, where they make them, and they all claim that they can explain all the binary black hole mergers ever seen in the universe. And now you seem to do the same. You say that at least 80% of the binary black hole mergers come from sort of cluster scenario. I mean, the rate you quote is consistent with the merger rate observed by LIGO. So who's wrong here, right? There must be at least 2 wrong, or everybody's right a little bit.
I think everybody is right a little bit.
So everybody's wrong a little bit too.
Yes. I mean, not wrong, uncertain. I think models are sufficiently unconstrained or sufficiently uncertain right now that you can twist them and twist the parameters even into unphysical parameters to reproduce the total merger rate. The thing is that there's models that are more naturally or with parameters that are more compatible with what we believe is right, with observations. There are models that have more affinity with producing some kind of mergers, and some models that have some more affinity to producing other kinds of mergers. I said, obviously eccentric mergers, dynamics are more likely to produce eccentric, or are the only channel to produce eccentric mergers. But also, I mentioned the mass. The high mass mergers are more natural in dynamics channels. So probably the answer lies in the middle, in the sense that lower mass mergers are produced in isolation and higher mass mergers are produced dynamically via hierarchical mergers or some other process.
Computer scientists call this uncertainty quantification, and astronomers call it systematic error bars. So what are your systematic error bars on your numbers? If you put your money on one of the scenarios, which one would it be?
And the total
Yeah, your own, of course, right? I mean, it's less dynamical scenario.
Sorry?
What would be your favorite?
In the rate. We're talking about the rate.
The rate. What is contributing to the most black hole mergers we have seen today? Which of the 3, 4, 5 scenarios you have?
I don't think I can make predictions for the ACN channel because it's extremely uncertain or very much more uncertain. I would say it's half and half of dynamics and of cluster dynamics and just isolated binary evolution.
And the galactic disk is out.
The ACN channel, it's very uncertain. I'm not an expert on that. I would say.
So, related to this, right? So you have many channels that produce eccentric binaries.
Yes.
And,
Those are triples, yeah.
right. And there is the Gen channel and
Yes.
potentially other ones as well. So is there a way to distinguish an eccentric binary that was formed from a binary-binary interaction compared to other binaries that are also eccentric and formed to other channels?
That's the, as I said before, there's this idea of the environmental effect, what they call in the group of Johann Samsing, and also in Tokenari, that they measure the effect of whatever's around. So another, the effect of the, in the gravitational wave, there can be some other way more dominant effects, such as the, for example, if it's a three-body interaction, the merging binary black hole may go around this third object that can be a black hole or a supermassive black hole in the tunnel or whatever, and this has some acceleration that can then be potentially be observable in the, as a phase shift in the gravitational wave data. Now, this could help us disentangle the formation channel potentially, but I'm not completely sure. In general, if it's dynamic, if it's eccentric, it comes from dynamics, but I'm not entering in whether it comes specifically from binary-binary interactions.
Perhaps a related question to Simon. So yeah, if we assume that there is this isolated binary channel, but then you also say that dynamics are important. So I mean, I like the isolated binary channel. So I mean, if we have these primordial binaries, how the production rate of this channel can be decreased, let's say, or how much does it change? It gets enhanced by dynamics, or it gets depleted by dynamics?
Okay, so in the isolated channel without it's by definition not affected by dynamics. So if we see some productions of, in this case, for example, lower mass mergers coming from dynamics, we know that the parameters of, let's say, in binary stellar evolution are over predicting the merger rate. So there may be an over-prediction of the merger rate in isolated binary evolution. And I think there may have been some paper pointing that out, that there may be some over-prediction of the merger rate. It's just a question of this, since everything, all the isolated and the dynamical channel are still uncertain, there's still work to do. The parameters may need some adjusting. For example, in the, let's say, the efficiency of the common envelope evolution or other parameters. So that's why dynamics can constrain binary stellar evolution.
Slight confusion maybe also in the also isolated binaries were born in clusters.
Yes, that's the paper. Yes, they can be born in clusters, but maybe they're just born in the outskirts of the cluster and very low
They are
cluster.
very massive. They have a sequence information.
Yeah.
So they are affected by dynamics. Any star is affected by dynamics.
No, true. Indeed. Yes. They will think maybe it's very short-lived clusters. Other than that, it will just come up in cluster models. So cluster models, any cluster simulation will also predict these sources.
How do you want to reduce the uncertainty in your models?
How do you want to reduce the uncertainty? Okay, good question. First of all, would be obtaining, or the most obvious way would be to obtain more data, gravitational wave data, and know not only the parameters that we observe in gravitational waves, so the masses, the effective spins, because we don't really measure spins, or etc., but also the correlation between the parameters.
Well, let me rephrase it then and ask, how much data do you need in order to demonstrate which of the models is right or what aspects have to be listed?
Ooh, okay. In general, I think, and I'm talking here, I'll talk about eccentricity because it's the smoking gun signal. We kind of have a prediction that some 5-10% of all mergers in clusters are eccentric. So we just need to be sure how many eccentric mergers have we observed. And then it's a simple calculation. So we need some, let's say, some years of eccentric merger analysis, and that we could disentangle isolated dynamics.
I had a couple more questions. So one is about the body models and Gaia binary. Yeah. So in your picture, you kind of have like binary versus binary single interactions, but I suppose that at some point also higher multiplicity systems will form, and then also triple interactions will take place, and also will become important to the formation of gravitational resources as well, but also energetic and the clusters. So I was wondering, like, if you have looked at this, or whether at some point also higher multiplicity systems will contribute and become important.
There may be important, but so what I found, and why I didn't look more into these systems, is that when you form in a binary interaction, you form a triple, and this undergoes a triple single interaction. Usually the triple is sufficiently wide that this system is unbound. This 4-body system, so triple single interaction is unbound. So it's very easily ionized. In an unbound system, there's no chaos, there's less chaos.
Almost triples they form, so binary interactions are actually solved. So that's what you're saying?
Yes, they dissolve in triple single interactions, further triple single interactions. And triple binary interactions, they're very much
But I
unlikely.
understand it's also true for binary, the binary that you form in binary. They undergo binary interactions. Yeah.
Some trigger mergers and some trigger triple formation. And these triples can undergo this triple single formation, but that is generally unbound. Yeah.
I have to look in on the binary triple interaction being very rare. There was just an interesting research on the runaways from R136, because as you mentioned before, that the runaways produced in that cluster, which is two binaries, both with masses of about 100 solar mass each, in a relatively wide orbit, 4, 6 AU or so, 4 or 5 AU, with very high velocities, and that was produced in a triple binary interaction. So the only encounter which you can trace back really to the cluster center and produce something like we show here was a binary triple interaction.
But that was the stars. Right?
Yes, that was before the interaction.
Okay. Yeah, that's different.
Well, I guess the reason we don't find binary triple interactions often is because the simulations don't start as triple.
Exactly. Yes. Yeah.
So this is a big assumption.
I mean, yeah, but also triple stars dissociate before they would have formed triple black holes that interact. So this is what we saw. We showed that the binary interactions are mostly of dynamically formed binary black holes. So I'm assuming it's the same. It's not the primordial binaries that interact. It's just the dynamically formed ones. And I think for triples, it would be the same. Even if we included triples in the simulations, you would have dissociation, then turning them into black holes, and yeah, three-body binary black hole interactions.
Okay, so a couple more questions related to the isolated binary. So yeah, you mentioned the lower mass black holes are likely these primary binaries, and like higher mass are dynamical, but that means that there is some sort of accumulation of mass, right? So there may be like some repeated mergers that make this black hole grow by repeated kind of mergers, like of the same black hole. So do you see that in your simulations that basically the same black hole undergoes like several iterative mergers that make it grow through history?
Yes. Well, I don't specifically look into that, but these are called the hierarchical mergers. So it's just two black holes merge, and this byproduct can merge again with another black hole. And yeah, this is something that's predicted. It's a bit more complicated because when the two black holes merge, they get some recoil, gravitational wave kick, that may drive the merger product out of the cluster. But if it doesn't, then it can come back and then merge. And it's likely to merge actually because it's very heavy, so it sinks to the center of the cluster, so it's likely to trigger another merger. This is also a channel that's proposed for the growth of intermediate mass black holes. That's something.
It's interesting to quantify that effect, to see if you can kind of reproduce this kind of like model distribution.
No, you can. Yeah, you do reproduce that.
So yeah, you also mentioned that the efficiency is higher in low-mass clusters, but these are also likely to evaporate faster, right? So then they don't contribute that much because
no,
they're shortly.
Even taking that into account, I'm not talking 100 solar masses. It's lower in 2 × 10⁵ here or 10⁵. So it's lower compared to 2 × 10⁶. But yeah, it's still not these 100 solar mass clusters. Which 100 solar mass cluster may not even produce a black hole. So, I mean, it has to be sufficiently wide as to have, sufficiently big as to have dynamics and black holes. So it has to have at least 4 black holes. So that still puts a lower bound if we want to have binary black hole interaction.
Okay, so you weight each cluster, but it's lifetime.
No, this is taking into account the number of mergers over all its lifetime. It's complete lifetime. And in these models we also take into account the different distribution in galactic-centric radius. So this based to the distance from the galactic center, which also influences the dissolution time.
Yeah, I think at one point you also showed kind of the cumulative distribution of X-ray binaries and everyday sources. Yeah, so let's say in your simulations where you're trying to reproduce the black hole 3, for example, so then you count kind of how many black hole 3-like systems you have a star kind of black hole binaries, right? But then my question is like, if you also are able to measure like X-ray-like sources from your simulation, just to see if kind of the distribution would match with the observed population?
I did not do that, but I matched it with LBK sources. I didn't. The calculator who ran the simulations originally matched this with LBK sources, so it matches. I'm not aware about whether this was matched with X-ray sources, but X-ray sources may also be coming from some isolated processes. I'm not entering into that. I know that the simulations are valid because of multiple tests that were done, including reproducing the LBK sources, and that these simulations reproduce
but it would be interesting, say, if you see those clusters with kind of an initial binary fraction, and then you let them evolve dynamically, if some dynamical process will disrupt this system, then let's say you will have less X-ray binary coming from these primordial channels. So then, let's say their numbers should.
I did not. It's of the scope. But that's in the paper that presented the simulation. There's some analysis, and I think that's technically X-ray binary. But yeah, I just.
That's not about well. Does the black line actually include selection biases? Because if you were to account for selection biases, then the black line would most probably look much more similar than to the red line. Right?
No, I think it's just getting a list of detections and putting them here.
Right.
This is not an illustrative of the. Well, this is an illustrative of what we see in LBK and what we see in the X-ray. not about the inherent.
Do you have to care about selection biases or to make this comparison or not?
Well, if this comes back to this, there are selection biases. I'm just saying these two methods of these two observational methods produce or observe two different populations, and this is the different what's observed. This is not talk about the inherent properties of the, because that is more uncertain. This has zero uncertainty. This is what we have detected so far. So zero uncertainty. But just an illustrative point.
Yeah. We are done with questions. Thank you very much for all the questions. And then we give the opportunity to the audience maybe to have a question or two, three, four. Anybody have a question? Yes, so I walk around.
Thanks very much for the very, very nice presentation. The committee has already stolen my first question, so I'll just ask about the mass ratio. This is another one of our sort of LDK things that we can measure. How strong, especially since you're looking more at lower mass fluxes and different types of interactions, how strong is the preference for the mergers to always be equal mass, or do you think from the things that you're predicting you'll see more of a distribution?
I don't think, well, my models do not really change the predictions that have been done so far in the mass ratio, let's say, scenario. Clusters generally tend to predict more equal mass mergers, as you said, than isolated binary evolution, but I don't think this changes with binary interactions. Not in a significant way. The smoking gun signal, as you said, is the eccentricity. So yeah, no change there. But yeah, preference towards equal mass mergers is a sign that kind of pushing it towards the dynamic side. Yeah. We kind of, or at least have done these projects trying to basically focus on this smoking acid.
Anybody else with a question?
How do the models depend on galaxy parameters? That is metallicity. Is it more or fewer?
These models depend on the metallicity of the cluster. We assume that all the stars in the cluster have the same metallicity, which is valid for dynamics. We've taken into account in this Monte Carlo simulation, we've taken into account different initial metallicities from 0.1 solar to 0.001 solar, and also the defining parameter is not the galaxy size, etc. It all comes down to a single parameter. It's for a fixed galaxy, it's the galactocentric radius, or some kind of the orbital frequency, and that's also taken into account. The model sample a distribution of these initial parameters, and one of the parameters that we consider is the distance. So the strength of the tidal effects produced by the galaxy. And we're also only considering circular orbits around the galaxy, but except in the case that it is very extreme, it's approximately, I think, for the dynamics effects at the very center of the cluster, this is not really too relevant. Because I said these effects or these outcomes happen at the very center of the cluster, which is the least affected by these tidal effects of the cluster.
So do you see more or fewer measures with metallicity, or it doesn't matter?
Less clusters with less metallicity tend to produce more measures.
Anybody else? the whole business here of asking questions. You can ask
Yeah,
questions in
yeah,
Spanish too,
yeah.
right?
Yeah.
The committee will not understand it.
Preguntas en español, catalán. Hay que ser doctor para hacer la pregunta.
No questions? Yeah.
Ayudo.
I'm PhD, but I haven't PhD, so
Well, I think formally,
It's not a question,
well,
right?
it's not a question to the candidate.
And in worst case scenario, we can discuss it outside.
Yeah.
Cool. Yes.
Formally, only doctors can ask questions during this question session.
I think we should then close the session, and I think you retire and we discuss here the marks and the whatever verdict of this committee. Thank you very much.
Thank you. Thank you too. Thank you to the people online. I will close the stream right now. And yeah, that's